Bismillahirrahmanirrahim. Hi everyone. I hope you are all doing well. I welcome you all to the class of real analysis. Our discussion is continue on chapter number 3, numerical sequences and series. Lastly, we discussed concept of convergent sequence and theorem 3.2. That is actually related to the properties of convergent sequences. In today's lecture, we will discuss an important theorem 3.2. This is also related to the properties of convergent sequences. So, firstly, we revise what is the definition of convergent sequence. A sequence AN is called convergent sequence, and it converges to A if for every positive real number epsilon there exists a positive integer n naught such that the difference, absolute difference of an minus a is less than epsilon for all n greater than or equal to n naught. So this is the definition of convergent sequence. I will use this definition to prove this theorem 3.3. This theorem says suppose Sn and Tn are the complex sequences. We have two sequences Sn and Tn, and it is given that the limit of Sn is S and limit of Tn is T. In other words, Sn converges to S and Tn converges to T. Then the first part is we have to show the limit of the sum of sequences is equal to sum of their limits. In other words, when you add up two sequences, then they converge to the sum of the limits S plus T. To prove this part, we have to show Sn plus Tn minus their limit S plus T. This absolute difference should be less than some positive real number epsilon whenever your n is greater than or equal to some positive integer n naught. So I will use the convergence of both sequences Sn and T. It is given that Sn converges to S and Tn converges to T. So by definition of convergence of sequences, for given epsilon greater than 0, there exists integer n1 and n2 such that I will use integer n1 for the sequence Sn, as Sn converges to S. So that's why the difference of Sn from its limit will be less than epsilon by 2 whenever your n is greater than or equal to n1. Similarly, Tn converges to T, so absolute difference of Tn and T should be less than epsilon by 2 for all n greater than or equal to n by 2. Here the important thing that you have to remember, whenever in the proof of convergence of sequences, you use two integers, two or more integers at the same time, then you have to take always the maximum of these integers. Why we are taking the maximum of these two integers? I want an integer that satisfies both of these inequalities. For example, if you say your n1 is suppose 10, n1 is 10, and suppose your n2 is 12. It means the first inequality, this inequality is true when your n is greater than or equal to 10, and the second inequality is true when your n is greater than or equal to 12. Now I want to ask, when both of the inequalities will hold, so what is the common value for which both of these inequality hold, the common value will be n greater than or equal to 12. And what is 12? 12 is actually the maximum of these two numbers. So that's why we are taking the maximum of these two integers. So put n is equal to maximum of n1 and n2 and consider this expression that we have to prove. So by rearranging, combining Sn with S and Tn with T, we have Sn minus S plus Tn minus T. By applying triangle inequality, this sum can be divided into two parts, Sn minus S plus Tn minus T. What is the triangle inequality for? In form of absolute, A plus B absolute is always less than or equal to A absolute plus B absolute. So according to this inequality, the first bracket represents A and the second bracket represents B. This is A and this is B. So now by using 1 and 2, Sn minus S, this is less than epsilon by 2 and this is also less than epsilon by 2 when n is greater than or equal to n. By adding these epsilon by 2, we have equal to epsilon. This implies this absolute difference is less than epsilon for all n greater than or equal to n. This shows that Sn plus Tn converges to S plus T, or we can say its limit is S plus T. And it completes the first part. Now we move towards second part. In its B part, we have to show limit of C times Sn is equal to Cs. In other words, if we multiply a sequence with a constant C, then its limit will be the constant time the limit of the sequence Sn. Similarly, if we add a constant C with each term of the sequence, then the limit of the new sequence will be C time plus limit of the original sequence, C plus S. So this B part has the two parts. Firstly, I will prove this part, and where C is any number. So we will consider two cases as C is any number. So in case if C is 0, then this sequence C times Sn, when you put C is equal to 0, this becomes 0, and similarly for C is equal to 0, the limit C into S, this is also 0. So Csn is equal to 0. So for every positive real number epsilon, there exists integer n naught greater than or equal to 1, such that the absolute difference. What we have to prove? We have to prove that its limit is Cs. For this, we will always consider the absolute difference Csn minus Cs, and we will show that this is less than some positive real number epsilon. So when you consider C times Sn minus Cs, as this is equal to 0, this is also 0, so their difference is 0. As epsilon is a positive real number, so clearly 0 will be less than epsilon for all n greater than or equal to n naught. So this shows that the limit of Csn is C times S. Now we consider the second case if your C is non-zero number. So when C is non-zero, then for positive real number epsilon, this quantity epsilon by C absolute, this will also greater than 0. So I have to solve this expression. So for this I have to show this is less than epsilon. So I will choose some expression in such a way that after cancelling this C, this expression becomes finally less than epsilon. So by using the convergence of the sequence Sn, there exists an integer n such that as Sn converges to S, so for every positive real number epsilon, and for this Sn I am setting epsilon equal to epsilon by C absolute. So this is less than epsilon by C by the convergence of Sn. Now consider what we have to show, Csn minus Cs, by applying the property of absolute. taking C common from absolute, this becomes C absolute Sn minus S. Now using this inequality, this is less than epsilon by C, and after cancelling C absolute with C, this becomes Csn minus Cs less than epsilon, and this shows that its limit is equal to Cs. Suppose in the start, if we not choose Sn minus S less than epsilon, we are discussing suppose at the start here, if I choose, if we set it as Sn converges to S, so for every positive real number epsilon, there exists a natural number n such that this is less than epsilon. We do not take epsilon by C here. Now what will happen here, when you solve this becomes C absolute, as this is less than epsilon, so this becomes C absolute times epsilon. Say this is the new epsilon equal to epsilon dash, as epsilon is a positive real number and C absolute is also positive, so this epsilon dash is also greater than 0. So in this way, Csn minus Cs is less than epsilon dash. So it is not necessary that if you are unable to find potential epsilon that can work for here, you can simply take epsilon like here. Next we show that this expression limit of C plus Sn is equal to C plus S. Case number 1, if C is equal to 0, when your C is 0 here, then simply this expression becomes limit 0 plus Sn equal to 0 plus S, or limit Sn equal to S, which is obvious by given assumption, because in the start of the theorem it is given that the limit of the sequence Sn is equal to S. So this result holds for C is equal to 0. Case number 2, if your C is not equal to 0, then for every positive real number epsilon, there exists a positive integer n such that Sn minus S is less than epsilon. This is the convergence of Sn. We have to show this expression should be less than epsilon. So consider C plus Sn minus C plus S. This becomes cancelling C. This is equal to Sn minus S. As Sn minus S is less than epsilon from here, this becomes less than epsilon. Hence, limit of this sequence is equal to C plus S. This is important. In this part, we have to show if the product of the two sequence is equal to the limit of the product of two sequences is equal to the product of their limit. To prove this theorem, I will use an identity. This identity says Sn into Tn minus St, that is the difference of these two expressions. This is simply equal to Sn minus S, that is the sequence Sn with its limit. This is Tn with its limit, plus S times Tn minus T, and plus T times Sn minus S. When you put here S, in the bracket we will write all terms in the form of T. When your outside is T, then in the bracket we will write all terms in the form of S. So given epsilon greater than 0, there are the integers n1 and n2 such that now I will use the convergence of Sn and Tn. So that's why I am taking here two integers n1 and n2. So at this time I will take this epsilon by square root of epsilon. Firstly, when we use the convergence of Sn, then for all n greater than or equal to n1 implies this should be less than some positive real number epsilon, and I am choosing my epsilon as in the form of square root. Similarly, for this sequence, I am again choosing my epsilon in the form of square root epsilon. As I have discussed above, when we take two or more than two times positive integers, then we will always take their maximum. So suppose the maximum of n1 and n2 is capital N. So this implies this product Sn minus S, Tn minus T is less than epsilon. How this is less than epsilon? Consider Sn minus S, Tn minus T. I want to show this product has a limit 0. So this is simply equal to Sn minus S into Tn minus T by using the property of absolute, which says x into y absolute is simply equal to x absolute into y absolute here. As Sn minus S, this is less than square root epsilon, and this is also less than square root epsilon. Whenever your n is greater than or equal to the maximum of these two numbers, that is capital N here. By multiply this is less than epsilon. So this shows that this complete expression, which is less than epsilon, shows the limit of this product is equal to 0 here. Also, from A and B part, as limit of Sn is equal to S, or in other words, we can say that the limit of this difference is equal to 0. Similarly, limit of this difference is equal to 0. So one gives after taking limit. Now, when you take limit in here at each part, this limit is equal to 0. This is also equal to 0. This is also equal to 0. So finally, this limit becomes 0, or you can say that the limit of this sequence is equal to St. The D part is also very important. In this part, we have to show the limit of the reciprocal of the sequence equal to the reciprocal of the limit, provided that Sn is not equal to 0 for any integer n. In other words, there is a no term in this sequence which is equal to 0 here. All of the terms are non-zero, and the limit is also non-zero. This also tells us that whenever in your sequence there is all the terms are non-zero, then it is not possible that its limit becomes 0. Then its limit will also be non-zero. In simple words, the limit of a non-zero sequence is also a non-zero. What we have to show? We have to show that this difference 1 over Sn minus 1 over S should be less than some positive real number epsilon. So to prove this theorem from start, first we will consider this part. This is the expression that I have to solve. By taking LCM, this becomes S minus Sn. In the denominator, we have Sn into S. By using the property A minus B absolute is equal to B minus A absolute, so this can be written as Sn minus S, and by separating the absolute over numerator and denominator, this becomes Sn absolute into S. Clearly, this term S absolute is a real number, but Sn absolute, this is not a single term, it depends on n. When you vary different values of n, it will give different values of this different term of the sequence. For example, for n is equal to 1, this is S1 absolute. For n is equal to 2, this is S2 absolute, up to so on. So this is not a single term, it entirely depend on the choice of n. So my first target is that I want to remove this term from here. I want this expression, I want my denominator independent from Sn. The first target is that I want a term which is independent from Sn, and it will be in the form of S absolute. Further, I want an epsilon for this nominator. So now we start here from here. Since Sn converges to S, it is given that S is non-zero. When S is non-zero, it means S is either negative or positive, but its absolute will always positive. So S absolute is positive. So I am choosing my epsilon as S absolute over 2 because epsilon is always a positive real number. So I have formed my epsilon as S absolute by 2, which is greater than 0. So for the convergence of Sn, there exists an integer n1 such that Sn minus S should be less than epsilon, and my epsilon is S absolute by 2 for all n greater than or equal to n1. Say this is inequality number 1. Now I want an expression in the form of Sn, as Sn can be written as by adding and subtracting the limit S. So this becomes S plus Sn minus S. This sum is always greater than or equal to a difference of these absolute. How we have a result, A absolute minus B absolute is always less than or equal to A plus B absolute, and which is further less than or equal to A plus B absolute. So applying this result here, this first number is A and the second bracket is B. So this A plus B is greater than or equal to A absolute minus B absolute. This is A absolute, this is B absolute. A absolute minus B absolute here. So this becomes Sn absolute greater than or equal to S absolute minus Sn minus absolute. Now using 1. In 1, Sn minus S absolute is less than S absolute by 2. Multiply 1 minus 1 on both sides, we have this becomes minus time Sn minus S is greater than, when you multiply this expression with negative 1, this will change the sign. This becomes minus S absolute over 2. Now adding S absolute here, on both sides, this becomes Sn minus S absolute greater than S absolute minus S absolute by 2. Clearly S absolute minus S absolute by 2, this is equal to half of S absolute. So this becomes Sn greater than S absolute by 2 when your n is greater than or equal to n1. Say this is 2. Now we consider the expression that we have to show, and I already explained this. This becomes here. Now I want to an expression from which we can remove Sn from the denominator. From 2, as Sn is greater than S absolute by 2, the denominator is Sn absolute into S absolute. So multiply both sides by S absolute here. This becomes Sn absolute, S absolute greater than S absolute by S absolute square by 2 here. Or after taking reciprocal, this becomes 1 over Sn absolute less than 2 over S absolute square. So substituting this reciprocal here in 3. So this becomes 1 over Sn minus 1 over S absolute less than Sn minus S absolute into 2 over S absolute square. Say this is 4. Lastly, again we will use this convergence of sequence Sn. So what will we set here? Epsilon here. That final term, this final term becomes epsilon. Again, using the convergence of Sn for epsilon greater than 0, there exists a positive integer n such that Sn minus S is less than, this is my new epsilon, that is S absolute square by 2 into epsilon, because when you substitute this epsilon here in the replacement of here, the final term in this inequality becomes epsilon. So put in 4, this becomes when you put S in the replacement of Sn minus S less than S absolute square by 2 into 2 over S absolute by square into epsilon. This will cancel and this is less than epsilon. That is required, and this shows that the limit of this sequence is 1 over S. So I hope now you have a clear understanding of this theorem. This is a very interesting and important theorem for your final exam. If you find this video helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.